Hello everyone, I'm Bertrand Tabuguia and I'm going to present a major result of my PhD thesis that I did under the supervision of Wolfram. This is power series representations of hypergeometric type functions. This talk relies on the following bibliography. For more details about this presentation, one can see my PhD thesis available on the Combra system of the University of Kassel. So now let's start the presentation. As outlined after an introduction where we give general definitions and backgrounds, we'll move on to the current maple status in computing power series. Then you will move to the presentation of a mean result, the computation of m-fold hypergeometric term solutions of ordinary recurrence equations. And in the last section, we will show how these can be used to compute hypergeometric type power series. So now let us introduce. To define what is a hypergeometric type function, we first recall what is a Laurent-Puiseux series. A Laurent-Puiseux series is a series whose starting point is an integer, here int 0, and the powers of the indeterminate variable is a fraction with bounded denominator k called the Puiseux number, which is a positive integer. A hypergeometric type power series is a linear combination of Laurent-Puiseux series whose coefficients are m-fold hypergeometric term. An m-fold hypergeometric term is characterized by relation 2, where Rn is a rational function. Note that when m is equal to 1, one talks about hypergeometric term. A hypergeometric type function is a function that can be expanded as a hypergeometric type power series. But note that we consider expressions that can be uniquely represented as we are using algorithmic approaches. So this diagram shows that holonomic functions can be studied to represent hypergeometric functions, polynomial functions, rational functions, and algebraic functions. What we call a holonomic function is a function that satisfies a linear homogeneous differential equation with polynomial coefficients. Such a differential equation is said to be holonomic. So it is therefore by computing power series solution of holonomic differential equations that we are able to compute hypergeometric represent functions either as hypergeometric type power series or as holonomic recurrence equations together with some initial values. But here we are interested in the case of hypergeometric type power series. In this family, as this diagram shows, is larger than the family of hypergeometric functions and therefore can be used to represent more the power series of more expressions. The computation of power series was formalized in 1992 by Wolfram Koepf, and the algorithm follows the following three main steps. In the first step, when you have an expression f, you compute a holonomic differential equation satisfied by that expression. And then in the second step, you convert that recurrence equation, that differential equation into a recurrence equations for the Taylor coefficients of, or the power series coefficient of the given expression. And finally, solve that recurrence equation. This is the step where the most difficult step, and in Wolfram Koepf paper, only a particular case of m-fold hypergeometric terms was considered. But now with my PhD thesis, we are able to compute m-fold hypergeometric term solution of linear recurrence equation, and also the computation of here of the linear combination needed to find the power series. Note that here also some particular steps are involved, like the computation of the Puiseux number or the starting point. By using such an approach, we are able to compute power series representations where the current formal power series module of Maple fails to find the representation. Here are two examples. In this presentation, I will describe and present a Maple implementation of our main ingredient algorithm m-fold hyper, and then also present, describe the FPS, the whole FPS algorithm, this is formal power series algorithm, with an implementation in Maxima, since I did my PhD thesis in the computer algebra system, Maxima. Let us now talk about the Maple status in computing power series. For computing differential equations, Maple used the code holonomic TE from the module formal power series, which is similar to the code find ODE of the DE tools package. As we use a different strategy at this step, we have our implementation called also holonomic TE from our module FPS. This is generally more efficient when more linearly independent terms are, we have many linearly independent terms in the input. For the computation of holonomic recurrence equations, this is straightforward from the previous step, but since these steps are dependent, we have our implementation called find RE. Now, since we are at the last step, you have to compute M4 hypergeometric term solutions of holonomic recurrence equations. The case M equal 1 is implemented in Maple as hypergeom solves by Mark van Hoes. And this algorithm is also needed somewhere in our ingredient. So we also have an implementation of it. And this was presented in the software demo at ICMS 2020. And from tests, we observed that our implementation of the variant that we described in my PhD thesis, a variant of Van Hoes algorithm, sometimes compute results where the RRE tools hypergeom solves fails. And you will see some examples here. Also, for the computation of starting point, Poisson number, and the linear combination needed to find the power series representation, we observed that due to some issue at this step, the current Maple implementation fails to find the representation. So let's see some example. We open Maple. Now, now here we start the package. We load the GE tools to show the timing. And here is to read our library. First, we compute a differential equation for this expression of Z. We have many linearly independent terms. Here is the timing, and here is the differential equation. One can observe that the coefficients here are not factorized, and we have this timing here. Using find ODE, we have this timing, which is beta, but the same differential equation of order 5, not factorized coefficients. And using our implementation, we have this timing, which is much better, and whatever the coefficients are factorized. So this is why we implemented our own algorithm. Now we want to show here how an example where hypergeom solves fails to find hypergeometric term solutions. Here it said there are no solutions, but however, using our implementation, we find that there are 2 hypergeometric terms solutions in the basis. Now here we give an example where the FPS command of Maple fails to find the power series representation, but where there are in the involved recurrence equation hypergeometric terms that can be easily computed using the hypergeom solves command. So this means that in the way of computing the linear combinations or the Poisson number of the representation, some things happen in the procedure. So here is an example where the starting point is missing in the given output, because the constant term here should be 1 instead of 0, as we can see from the Taylor expansion of order 0 here. So this is the Maple status actually, and the problem that we can find in their implementations. Now let's go to the presentation of our main ingredient in the third section, computation of M4 hypergeometric term solutions of holonomic recurrence equations. We have this generic recurrence equation, and we want to compute a basis of the subsets of all M4 hypergeometric term solutions. Here, M is a positive integer. An M4 hypergeometric term can be seen in M different ways, here represented by the index J. And from any representation, the order representation can be deduced for that, and these represent all the dimensions of the solutions. For this presentation, we will consider the case J is equal to 0, and note that we can always deduce the order representations. And this is the difference for our methods and the other methods generally used to compute M4 hypergeometric terms. Because here we focus on one dimension instead of all the other dimension. Whereas in the method that usually compute right factor of recurrence equation, their approach generally try to compute all the dimension at once, and this sometimes involve non-commutative algebra and make things quite difficult. So first of all, we want to bound the value of M, and we have the following lemma that allows us to bound the value of m with the order of the recurrence equation. So this means that m-fold hypergeometric terms solutions of a given recurrence equation has the value of m less than the order. Now, after this lemma, let us introduce some definitions. The first definition is a definition of m-fold, what we call m-fold holonomic recurrence equation. An m-fold holonomic recurrence equation is a recurrence equation with at least two terms and whose indices of the indeterminate sequence have the differences as a multiple of m. As examples, here we have a two-fold holonomic recurrence equation and a four-fold holonomic recurrence equation. As you can see here, if you take, for example, n plus 6 and n plus 4, the difference is 2, which is a multiple of 2, and this happens with all the order n6. The same with the four-fold holonomic recurrence equations. So what is our idea? Our idea is to compute m-fold hypergeometric terms as we do for hypergeometric terms. And to do so, here is a change of variable that we use to transform a given m-fold holonomic recurrence equations into a one-fold holonomic recurrence equations and use an algorithm that can compute hypergeometric terms. So this way, if we consider, for example, our two-fold holonomic recurrence equations, by changing the variable as here presented, all the n become 2k and the a2k become sk, then the recurrence equations becomes this recurrence equation here, and using an algorithm to compute a hypergeometric term solution, we find the space of solution, and replacing k by n, we find the space of solution for a to n. So this solves the issue of m-fold holonomic recurrence equations. Now, how to generalize this for an arbitrary holonomic recurrence equation? For that purpose, we introduce again two definitions. This is m-fold holonomic distinct and m-fold holonomic equivalent recurrence equations. Two m-fold holonomic equations are said to be m-fold equivalent if any index taken from one recurrence equation and another taken from the other recurrence equations have the difference as a multiple of m. And the m-fold distinct is the opposite of that definition. Let's see this from some examples. Here we have three-fold holonomic distinct and three-fold holonomic recurrence equations. And if you consider, for example, RE1 and RE2, you take any terms from this recurrence equation, for example, an plus 11 and here an plus 7, the difference is 4, which is not a multiple of 3. And this happens with all the order indices. And this shows that RE1 and RE2 are three-fold holonomic distinct. But if you consider RE1 and RE3, you will see that the difference is always a multiple of 3. And this shows that RE1 and RE3 are threefold equivalent. Now, a major result of my PhD thesis, which is the main result of this presentation, is this theorem which gives a structure of holonomic recurrence equations that have m-fold hypergeometric term solutions. If you fix m and you consider an m-fold hypergeometric term Hn, the theorem says that Hn is a solution of a given holonomic recurrence equation if that recurrence equation can be written as a linear combination of m-fold holonomic distant recurrence equations that have Hn as a solution. And this theorem leads us to an algorithm that we call m-fold hyper to compute all the possible m-fold hypergeometric term solutions of a given recurrence equations. The algorithm goes as follows. We have a recurrence equation. We iterate m from 1 to the order of the recurrence equation and compute at each step, when possible, the m-fold holonomic, m-fold hypergeometric term solutions of m-fold holonomic distant recurrence equations involved. Let's take our previous example of two-fold holonomic recurrence equation. It turns out that we also have four-fold hypergeometric term solutions. In fact, these recurrence equations can be written as a linear combination of the recurrence of these two recurrence equations that have the same subspace of four-fold hypergeometric term solutions, and therefore the corresponding hypergeometric terms are the solutions needed for the four-fold case. And finally, since they are not order m-fold linear combination of n-fold holonomic distant linear combination for 5 and for 6, we deduce the space of solutions, which is this one, 2-fold and 4-fold. For the other examples, which was the 4-fold recurrence equation, we have 4-fold and 8-fold hypergeometric term solutions. Note that, in fact, these bases of solution represent the necessary basis to compute the coefficients of the power series of exponential of z squared plus cosine z squared and exponential of z squared plus cosine z4 times sine z4. Let's do some computation using our Koepf Maple implementation of this algorithm. We are using, as you see, the Maple 2019. So now we read our library on the directory. We compute a recurrence equation for this expression here and compute the corresponding m-fold hypergeometric term solutions. We have 2, 4, and 6-fold. Here is a recurrence equation for this expression. And computing the m-fold hypergeometric term solution, we have 2, 3, and 4-fold. Another example here, and if you compute the solution, we have 1-fold and 2 2-fold hypergeometric term solutions. These are some computations. Now, let's talk about the computation of power series. We consider a kind of generalized family of expressions. Note that every hypergeometric type function is holonomic, so we can use our procedure. Now, a kind of generalized is to say that the given expression might not be analytic at the point of expansion, since the t of z here sometimes involve log of z, the log of z term and negative power of z. So our approach is a kind of generalized computation of power series, and we will see it from some examples. Here is arctangent of z cubed plus log of 1 plus z squared. We compute this recurrence equation from these differential equations, the recurrence equation for order 10, and then we use m-fold hyper to compute m-fold hypergeometric term solutions. We have 2-fold and 6-fold hypergeometric term solutions. We use m-fold hyper again to find the order representation of the solutions. This is straightforward from this one. We have the even and the odd, and for the 6-fold we have 6n until 6n plus 5. So now we look for the linear combination to find the representation. We have established a certain formula to compute the minimal order to be used to find the linear combination whenever it exists. This is the minimal order of the Taylor expansion. And from this computation, we are able to find here the representation of the power series of arctangent of z cubed per log of 1 plus z squared. Let's just consider a more general example. Here we have f of z as 1 plus z squared times exponential of z plus arc secant of square root of z. Here the square root will involve some Poisson numbers. We have this recurrence equation here. Now to compute the starting point and the Poisson number, we have established also some lemmas and property that shows that the Poisson number can be computed as the least common multiple of the rational root denominators of the leading and trailing polynomial coefficients, and the starting point can generally be taken as the maximum integer root incremented by 1. So using that fact, here we have the Poisson number is equal to 2, and now we compute the recurrence equation for f of z squared. This gives this recurrence equation here, and from this recurrence equation we found the starting point is equal to 1, and this will be used to compute the Taylor expansion of order 1, which will give that terms here, and we will compute the power series of f of z squared in the same way as we did previously. And finally, substitute z by the square root of z to find the power series representation of f of z. So this is basically how the algorithm works. Let's see some computation using our Maxima implementation, which is quite complete compared to our Maple's one. Here we load our package. We compute the power series of exponential square root of z plus log of 1 plus square root of z. Sometimes Maxima does not display the summation symbol, but here is the representation, which is fine. And here we have another expression. I like this one, which is the log of 1 plus z squared plus z cubed. It is difficult to see that we can have 2-fold and 1-fold from this expression here. And here we have a linear combination of 2 hypergeometric type functions. which give this one here. And you can see the M4 hyper algorithm linearizes the computation of power series. We have this one which corresponds to this, and this one which corresponds to this. Note that all these computations cannot be rendered by the current implementation of Maple. So this ends our presentation. Thanks for watching. I hope you enjoyed.